Hello everyone, welcome to another instructional video for our homework for studying for the DC circuits and E-fields mini exam that I plan on giving you on tomorrow, Wednesday. I'm assuming that by now you will have already done all these problems that I'm about to show you. So if you haven't, please feel free, the problems are all in this video, please feel free to take a break, try the problem yourself first, and then watch me do the solution. Okay? You should really try and do these yourself. You will not learn as much if you just watch the video and don't try it yourself. Alright. That being said, here we go. This problem is actually very short and simple. There's only one mistake. Determine the E field, or the electric potential, at a distance r above a point directly between an electric dipole. An electric dipole is just two charges. That's called a dipole, which consists of an object of charge plus q on the left and a second object of charge minus q that is a distance r to the right of plus q. Okay. So to find the V field, the electric potential at a point, we use the equation from a point particle. Okay, we use the equation kq over r, where k is our, good constant, 9 times 10 to the 9. Q is the charge of the source charge, and r is the distance away from the source charge to the point that we're looking at. In this case, we've got two source charges, so we're going to have to do one of these for the plus and one of these for the minus. Our point is right here. It's an equal distance between the two charges. The distance between these two is r, which means that the distance from each charge to the middle here is r over 2, and then the distance in the y direction is just r. So if you look at the mathematical representation solution here, you see that we've got just the sum of the two potentials. If you remember, electric potential is not a vector like E field is, so we can just simply add them, so to speak. So we've got k and q. This is, I guess, the one for plus q, and this is the one for minus q. Kq over the distance r. Now, because this is r and this is r over 2, we need to find this distance here, which is represented here. It's just the hypotenuse, the square root of r over 2 squared plus r squared. This is both correct. This one's correct. The only mistake here is this part right here. Okay? This just doesn't make any sense here. There's no need for this to be here. There's no other way of explaining it. If this were an E field and both the charges were the same, then you could talk about the force between them, but then there would be no negative sign. So the squared is the only thing that's wrong there. So in your explanation, the representations are not the same just because of this guy here, right? Because this is our equation and there's no squared here. That's it. Simple as that. See, not so bad. Moving on. Determine the speed of the dust particle illustrated in the table that follows. So it is a 0.001 gram dust particle charged to 1 times 10 to the negative 7th coulombs and encounters a uniform 1 times 10 to the 4th nanocoulomb electric field, as shown. Determine the change in its speed after it moves a vertical distance of 1 meter. So we already have this distance from here to here, which we're saying is 1 meter. Now, there would be several ways of determining this problem. We can use dynamics and say if there is a object, right? Right now it's experiencing two forces, technically. One force of Earth on the particle and one force of the E field on particle, right? We would then add these two forces together, solve for the acceleration, then use kinematics. If it's not moving, we're assuming, then if it starts with a 0 velocity, then find the final velocity. I don't like that because that takes a long time. So what I'm going to do is I'm actually going to use energy to solve this, because if we assume that after 1 meter it has reached some sort of 0 reference point, so to speak, then we know that up here it started off with some gravitational potential energy, and the E field was also doing some work to help it move also. So we're given the 1 meter, we can calculate the force. So from this, we can find the final kinetic energy at the bottom here. So just to illustrate that in a bar chart, we've got our bar chart here. If our system is just going to be the Earth and the particle, then all it has is gravitational potential initial, work, and gravitational potential final. And we can talk about the work done in terms of the force that's exerted on it. So it starts off with some gravitational potential energy. It ends up with no gravitational potential energy. And we got to talk about kinetic also. Sorry. Kinetic initial, kinetic final. It has 0 kinetic energy here. There's also some work done by the E field, probably much more than the gravitational potential energy it had initially, but then all of this ends up as kinetic energy at the end. Okay, so to represent mathematically, so I'm just going to take all of my equations. We've got UG initial, this is plus equals plus. UG initial plus work is equal to kinetic final. So UG initial is, well, MGH, don't know what happened there, plus work, which is force E field times distance, and the kinetic final, which is 1/2 mv squared. Now, we can we cancel anything out here? No, we cannot. So, we will substitute in for our force. Now, if you recall on the equation sheet, force of an E field, right, on an object is just going to be Q, the charge, times the E field strength, of which both we are given. So, mgh plus QED is equal to 1/2 mv squared. From here, we will just plug in all of our numbers and solve for the final velocity. I'm not going to go through that. I think you guys know how to plug numbers into a calculator. Now, indicate any assumptions that you made. One big assumption that we made is that V initial is equal to 0. Okay, if it wasn't, it'd be easy enough to solve for to plug it in here and find out what it is, but we're assuming that it is 0. We are assuming a uniform E field. Okay, if it was not a uniform E field, then the force that it exerts would change based on the distance, and we'd have to use electric potential energy instead of work. But because this force, we're assuming, therefore, that this force, this leads us to say that F is constant. Right? We're saying that this is a uniform E field, so the force that it exerts is constant, which is why we can account for the work that is done. And that's about it. Oh, obviously, I mean, maybe not obviously, but we're assuming no air resistance. It is only a dust particle, so it's entirely possible that I could experience some air resistance, but we're assuming no air resistance. And of course, we assume that Yonatan is frictionless. Anyway, so that's that. Moving on. All right. So, determine the electric potential at point A. So we're looking for V at this point here. Specify your choice of the reference point where the potential is 0. Okay? 3 charged objects are shown. Determine the electric potential V at point A. That is at a position of x is equal to 0.9 meters. So, based on this representation, what we can see is that this charge has 2 times 10 to the negative 6 coulombs and is at our 0, this is at our origin. Then at 0.3 meters here, we've got a negative charge of 4 times 10 to the negative 6. And at 0.6 meters, we've got a charge of 2 times 10 to the negative 6, like this one. And we are looking for the potential here. So, because it is potential, that's very easy. We can just say that the potential is just equal to the sum, right, of KQ over R. Since K is constant, we can take that out of the equation. So we'll just say that this is equal to K times the sum of Q over R's. Right? That's basically it. So we've got k times q1 over delta x1, which in this case would be 0.9, right? q1 over delta, we'll call this delta x1, so the distance from x1 to a, minus, because this is a negative, q2 over delta x2, again, delta x being the distance from x2 to xa, plus q3 over delta x3. All right, so plugging in here, we've got, I'm just going to go outside the box here, v is equal to, well, k, which is 9 times 10 to the 9th. I'm just going to go outside the box here. So v is equal to, just going to go outside the box here. So v is equal to 9 times 10 to the 9th newtons meters squared per coulomb squared times q1, which is 2 times 10 to the negative 6, over delta x1, which is going to be 0.9 meters, obviously, this is coulombs, minus q2, which is 4 times 10 to the negative 6 coulombs, over the distance from q2 q2 to our point here, which is going to be 0.6 meters, plus another 2 times 10 to the negative 6 coulombs over this final distance, which is going to be 0.3 meters. All right, and plugging all that in, we get roughly 20,000 volts. All right, that's going to be our potential at that point from those three charges. That's a lot. All right, and of course, specify your reference point where the potential is 0. So we will assume that at some distance infinite away, v is equal to 0. So the amount of work we would have to do to get a charge from here to here would be about 20,000 volts over or times that charge that we move that distance. All right, and remember, volts, this represents the joules per coulomb that we put here, right? So if you were to put a charge of, I don't know, half a coulomb here, right? If you were to put some charge here, there is none here, this is just a point in space. But if you were to put some charge at this point, then because this point has a potential of 20,000 joules per coulomb, if you put half a coulomb here, you would have 10,000 joules of energy between this charge and this system of three charges. All right, moving right on down. All right, another evaluate the solution. So imagine two electrically charged objects plus Q and minus Q connected by a plastic rod, not shown in the illustration, of length L. Plastic meaning that they're insulated from each other, the charge cannot transfer. Write an expression for the electric potential at position 1, distance r to the left of plus Q, position 2, and position 3 at their respective distances. Identify and correct any errors in the solutions in the table that follows. So, looking at this, we've got the two charges that are separated by a length L, and we know that point 1 is a distance r to the left of plus Q. Position 2 is halfway between the two charges, so L over 2. And position 3, which is r to the right of negative Q. So, let's look at their solutions. Now, one thing that I am reluctant to state is that 1/2 of L is equal to R, okay? Just because it looks like it here does not mean that that is true. All right? Yeah, it is not fair to assume that. So in the solution, if at any point it says that something is several distances of R away from another one, it is not fair to assume that because we don't know that. So for example, in this problem right here, okay, so we've got two charges which means we're going to have the potential from one charge and the potential from another. I notice right off the bat in V1 that they're using squared, which is not allowed. That is not the equation. V, if you recall, which we just used in the last problem, is kq over r, right, where r is the distance between the point and the charge. So already that's one mistake here. So r is not squared. Kq over r here is fine. That is the potential from the positive charge. Plus k negative q over 2r. So here this person defined the distance from negative q to this as 2r. That's not true. That would be, the r negative would be r plus L. That is what I would use for the correct solution. In this one, again, it's saying r over 2, r over 2. The rest of this is fine, but I would call this L over 2. So r does not equal to L over 2. That is an assumption that you would be making. And then finally, in this last one, again, it's saying that the distance between the plus q and 0.3 is 2r. Okay, at least it's not squared this time. Oh, but in this one first, sorry. Otherwise, everything is correct. So it's still L over 2 and L over 2, and therefore the potential between them is going to be 0 at exactly in the middle. So that one is, the rest of that is fine. And in this one, again, it's defining the distance here. 2r does not equal L plus r, all right, which is what it is. And this kq over r would be fine, except this has to be negative because it is a negative charge here. All right. Otherwise, and then you'd have to, fix the math that goes along with that. Again, I'm not going to do that because there's no need to. You can plug this in yourself. If the equation that you do come up with is not as eloquent looking as this, then that's fine as long as you did the math correctly. All right, and last problem for this set. Now, I know this one's a doozy. There's a lot of reading, so that is the hardest part. So read through it, bear with me, come back in a minute, and then we will look through it. And we're back. So I'm assuming that you have read the problem and have analyzed it the way I did. So here we have a picture of what I think the scenario looks like. We've got this smokestack with smoke particles coming up here, moving at 5 meters per second. Vy specifically equals 5 meters per second. And we know that they're 20 meters high. We know that the E field here is 3,000 newtons per coulomb. Now, I know you're saying to yourself, well, when I read the problem thoroughly, I saw that it said the E field strength was 3,000 volts per meter. I just want to bring your attention to something, a quick unit analysis, volts per meter. So volts per meter, volts, if you remember, is joules per coulomb times 1 over meters, right? And a joule, if you remember, work, right? Work is something that allows you to give something energy, is a physical quantity that means how much energy you've given something. Work is force times distance, which means that joules can also be expressed as newtons times meters over coulombs times 1 over meters. Meters cancel out, and what you're left with is newtons per coulomb. So volts per meter is just a fancy way of saying 3,000 newtons per coulomb. Just wanted to make sure to get that out there. All right, now, so there's this 3,000 Newton per Coulomb E field, 20 meters high. The mass of the particle can be anywhere from 1 times 10 to the negative 9 kilograms or 1 times 10 to the negative 7 kilograms. That is the 1 microgram for this one or 100 micrograms for this one. I just converted to kilograms because the ionizing charge, in other words, when you ionize something, you give something a charge. So this charge is 1 times 10 to the negative 5th coulombs per kilogram that it ionizes it with. So we would have to find out what the kilograms are and then multiply these two to figure out what the actual charge on the particles is going to be, so that we can then figure out later on what happens. So what I picture happening is this. you have these particles moving with some velocity up. They encounter this E field here, and then as they go up, they sort of drift to the side when they enter the field. Okay? Now, this system will only work if for the heaviest particle, right, the heaviest one starting from the furthest away from the side that it's being ionized to, or that it's being deflected to, will stay inside the chimney, will not surpass 20 meters by the time it travels this distance, right? So again, this particle here, which I'm assuming is the heaviest one, all right, this 1 times 10 to the negative 7 kilograms with this much charge on it, that if it starts all the way to the wrong side, so it's not near this wall, it's near this wall, and it passes through our E field, that even though it is the heaviest one and lasts in this E field, that it will still not make it the full 20 meters out. So essentially what this becomes is almost sort of a projectile motion problem. If you picture this turned on its side, right, what you've got is almost projectile motion, right? You've got something traveling like this. Only this time, instead of the force of Earth exerting a force down on it, you've got this E field exerting a force down on it, causing it to accelerate down. Also, one of the assumptions we're making is that this E field is exerted the entire way through the smokestack, which I'm sure it's not, but let's say it is for the sake of argument, because if this E field is being applied the entire length of the smokestack and the particle still makes it out, then obviously the smokestack's not being very effective. If it doesn't even get close, then maybe we can say how far or how big the E field thing needs to be so that it does work. I don't know. We'll figure it out. So let's start with the force that is being exerted on this particle, right? So we know that the E field strength, or that the force of the E field on the particle is going to be Q times the E field strength. And we remember this is not Q, this is the charge per kilogram. So to find Q, we'd have to take the mass and multiply it by this charge density to find the actual charge. So Q is going to be 1 times 10 to the negative 7 kilograms times 1 times 10 to the negative 5th coulombs per kilogram times the E field strength, which is 3,000 newtons per coulomb. Right? And let's see, doing some quick math, we've got 1 times 10 to the negative 7 times 1 times 10 to the negative 5, which is 1 times 10 to the negative 12, times 3,000, which is going to be 12, 11, 10, 9. So 3 times 10 to the negative 9 newtons. That is the force that is being exerted on our particle from this E field. Okay, now that we have that, we know that the Vy initial, this is just essentially a kinematics problem. I know I say never to use that, but in this case it's projectile, so you kind of have to. Vy initial is going to be 5 meters per second, and we're assuming this is constant. We will assume that Vx initial is 0, right? So the x direction being this way, right? If we call this y and this x, we'll make this positive, make this positive. We are also sort of assuming that there is no gravitational force on these teeny tiny particles. It's not going to be anything compared to the electrostatic force that's being exerted on it. So I'm ignoring the force of Earth on these particles for now. We can maybe add that in a little bit later, but I'm going to ignore it for now. And finally, we've got, if we know that our force is this, then our acceleration in the x direction is going to be the sum of the forces, which is just the electrostatic force, so that's 3 times 10 to the negative 9 newtons, over the mass of our particle, which is 1 times 10 to the negative 7, which means that this is going to be 3 times 10 to the negative 2 meters per second squared, right? So, and our delta x is going to be 0.3 meters here. So the first thing we need to do in a kinematics, in a projectile problem, is we need to find out how much time it's going to take this particle to travel the full distance down. All right, the same thing that we would do in a projectile problem. We'd have to find out how much time it takes to get from the launching point to the ground, and then use that time to find out what the horizontal distance is. This time we're doing it the same way, just flipped right side up. So we know that, well, delta x is going to be 1/2 at squared plus v initial. We said that vx initial is 0, so it doesn't matter. So then our time is just going to be 2 delta x over a square root, which is going to give us 2 times 0.3 meters over 3 times 10 to the negative 2 meters per second squared. And this is all square rooted, which gives us a time of, this will give us a time of roughly 4.5 seconds. That's quite a bit of time. All right, now that we have the time, we can plug that into our delta y equation. In this case, again, I'm still assuming that this is going to be a constant velocity. Delta y is just going to be y initial, which we'll say is 0, plus v initial t. In this case, v initial was 5 meters per second, and t was 4.5 seconds. And we get from that 22.5 meters. Now, that is assuming that this force is being applied the entire length of the smokestack, which seems thoroughly inefficient. So on the question, will you recommend that the operating license for your smokestack be renewed? I would say 100 times yes. The heaviest particles are making it out of the smokestack, even if this E field is applied the entire way. We could do analysis of the lighter ones, but I think it's safe to assume that those might not make it out. But this, again, is based off the assumption that this E field is applied the entire way. Since I'm assuming that the E field is only applied for a short period of time, then who knows if those particles will even make it out, or would not make it out. So I would say yes, for sure, because of this reason right here. All right, I'm going to stop here for this segment. This was the E field problems. I'm going to move to chapter 16 on the next one. So see you there.